The last day of Chem1B before the final exam. The final exam will be two parts. Part one is the take-home part. That's due 1 week from today at 8 a.m. The take-home portion of the final exam is currently posted on the Chem1B website. For the take-home portion, you can work with other students. If you discuss any portion of the take-home portion of the final exam with another student, that means that you need to work in a group. You can turn in one set of solutions with the names of all the people in your group. I should also say that on the take-home portion, questions 1 through 4 you can work with other students. Question 5 you need to do on your own. And then the second part of the final exam is an in-class part. That'll be 1 week from today from 8 to 11. That's open book and open notes. And that portion of the exam should be done by yourself. The final exam is comprehensive. Okay, so let's see. Last week we just finished discussing nuclear chemistry. So for the most part, we talked about radioactive decay and nuclear fission. So although this slide here talks about nuclear fusion, I won't ask you any questions about nuclear fusion on the exam. So if you're interested, you can take a look at these links on the fusion reaction in the sun. How atoms were made in this nucleosynthesis reaction and the Big Bang. And you can also look at nuclear fusion reactors. And you can also look at radioactive isotopes used in nuclear medicine for diagnosis and therapy. There might be a question on the take-home portion of the final exam on nuclear medicine. And this is just practice, so we can skip that part. Okay, so last section, the last topic we'll discuss in Chem1B is coordination compounds. So it turns out that most compounds will contain main group elements that are either white or black. Many transition metal compounds are colored. Okay, so they're either yellow or green or blue or pink or whatever. For example, gemstones are colored, rubies are red. So does anyone know why rubies are red?
The color there, the wavelength of light inside.
Yeah, so what's inside rubies that's make it red?
Transition metals.
Good, yeah, so it's transition metals. It turns out there's chromium in ruby. So it turns out that ruby is alumina, which is Al2O3. And there's a small amount of chromium 3+ impurities in the alumina. It's actually the chromium 3+ impurities makes the ruby red. So what happens is that some chromium 3+ substitutes for the aluminum. So now you have this chromium surrounded by 6 oxide ions. And when electronic transitions occur from one energy state to another, that turns ruby red. Okay, so really when we change a metal, for example, from a main group metal to a transition metal, it changes the color of that substance. Here's another example. You can look at this in Lab 4 this semester. Dry red is the color indicator in drying agents. So when dry red is added, which is a cobalt chloride compound, blue means that the drying agent is dry, pink means it's wet. So when it's blue, it's actually this compound here. So you have cobalt surrounded by 4 chloride ions as well as 2 water molecules. And then when it gets wet, you actually have more water. So some water substitutes for the chlorine. And now you have 6 water molecules surrounding cobalt, and then it turns pink. Okay, so note by changing the substance bonded to cobalt, that changes the color of that compound. So let's do this for practice. Write an equilibrium equation that represents this reaction. Once you write that equilibrium equation, share it with the person sitting next to you and see if you come up with the same equation. Okay, so share your equilibrium equation with the person sitting next to you. See if you came to the same answer. Okay, so there's our equilibrium reaction symbol. So what goes on the reactant side?
CO4.
Okay. So yes, we can write COCl4. Let's see, that has a -2 charge, aqueous. Okay, anything else go on the reactant side?
Water.
Plus what? Water, okay. How many waters should we put on there? Now, how many waters should we put on there? Two. Just one? Two?
I think you cancel that anyways.
What goes on the product side?
CO2 plus.
Okay, so CO2 plus aqueous, and then what else goes on there?
Or CO.
Plus what?
CO. Or CO.
And how many chlorides? Four. Okay, now this is one way we can write it. Another way we can write it is based on the structure. So note that in cobalt here, there's 4 chlorides. There's 4 chlorides and 2 waters. So when we say COCl4 2 minus aqueous, we can also write this with COCl4 H2O2. And then the charge on this compound is -2. Okay, and then this reacts with water. And then for the CO2 plus aqueous, note that there's 6 water molecules surrounding the cobalt, so we can write it this way. And is this equation balanced? Let's see, on the product side we have 6 waters. On the reactant side we have 1 plus 2, 3 waters. So waters aren't balanced now. So to balance this equilibrium reaction, we need to have what?
More molecules on that.
Yeah, so we need to have 4 water molecules. Are the chlorides balanced? Yes, they're balanced. Is the charge balanced? Remember we were looking at conservation of charge with oxidation reduction reactions? Yeah. Although this is not an oxidation reduction reaction, the charge should also be balanced. So is the charge balanced?
Yes.
Yeah, because note that we have a -2 charge from this compound. On the reactant side, we have a +2, -4, and that's equal to -2, so the charge is balanced. Okay, so this is our balanced equilibrium reaction. So note again that by adding water and applying the Lechette-Deliet's principle, this shifts the reaction toward the product side. And how can we shift this reaction back toward the reactant side?
Water.
By doing what, George?
Take away the water.
And how do you take away the water?
Add more chlorine?
Yeah, so one way is by adding chloride ion. What's another way to shift this reaction back toward the reactant side? When you do this in lab,
You can add more water?
if you add more water, that shifts it back toward the product side. Right? So this reaction turned out to be, as most reactions are, that's exothermic. So if you do what? Yes, if you heat it up, that's going to make the reaction go back toward the the reactant. So that's actually a way to regenerate the dry-rite. It's just by, when it turns pink, just heat it up. That removes the water, and then you get your pink, and you can use your drying agent again. So a drying agent is used just to remove water from a substance. Okay, here's another one. The color of meat depends on the substance that binds to myoglobin. Now, myoglobin is a protein, and it turns out that the middle of that protein is iron. So it turns out that oxygen binds to iron, or water binds to the iron in myoglobin, or in this case here, CO, carbon monoxide, binds to the iron. So note that when oxygen binds to iron, the color of myoglobin is red. When water binds to the iron in myoglobin, it's brown. When carbon monoxide binds to the iron in myoglobin, it's red. So there's a couple things that's happening here. So note that the charge is different. So if we change the charge, it changes the color. If we change the substance bond to iron, that also changes the color. So this is one thing that meat packers may or may not do to keep the meat red on the shelves, is they may expose the meat to carbon monoxide just to keep the meat red.
Okay. Does it mean it's fresh then? Huh?
So it looks, yeah. So it looks fresh. As opposed to brown meat, you look at that on the shelves, you say, that's not so fresh. I'm not sure. I'll skip that one. But it may be. London.
So then the brown meat might be fresher than the red meat.
Yeah. Yeah. Now this is for raw meat. Now it's different when you cook the meat. So when you cook the meat, note that one thing that happens when you cook meat, which is protein, is what? So when you heat up the protein, what happens to the protein?
Denatured.
It gets denatured. Okay, so you change the folding in that protein, and that's also going to affect the color of the meat. Actually, this is the lab I wanted to do for the last lab of the semester. You bring in some red meat. We'll see what we need to do to change the color of the meat. But we ran out of time, so maybe another time. Okay, so what's happening here now? In Chem 1A and so far in Chem 1B, we talked about covalent bonds. We know that a covalent bond forms when one unpaired electron from one atom combines with one unpaired electron from another atom. And this line between the two atoms represents a bonding pair or a covalent bond. Now in this case here is that, are those electrons in the bond equally shared between the H and the Cl? And how do we know they're not equally shared? Yeah, so the property that we need to look at is electronegativity. Now, when a metal, in Chem 1A we said that when a metal bonds to a non-metal, what type of bond is formed? An ionic bond. Well, it turns out that covalent bonds can form between a metal and a non-metal, and that depends on the electronegativity difference between the metal and non-metal. So when a covalent bond forms between a metal and non-metal, that's called a coordinate covalent bond. So for example, if we have this non-metal, I'll call it L, and note that there's a lone pair on this non-metal. This lone pair can bond to the metal, and that's called a coordinate covalent bond because the bonding pair, in this case here, comes from the same atom. Okay, so really, these are covalent bonds in each case, but the difference is where the electrons come from. So again, in a covalent bond, you get electrons from each atom. In a coordinate covalent bond, the electrons come from one atom only. Okay, so in this case here, we call M the metal. So for the non-metal, that's often called the ligand. Okay, so here's a comparison of coordination compounds compared to organic compounds. So in organic chemistry, we look at the chemistry